Welcome everybody. My name is Per Salin, and you've seen me at these webinars. I'm the CEO of EQUA, and you've also met our other speaker today, Sven Moosberger. He's the CEO of our German and Dach company. And the third speaker you have seen in the past, but not recently, I don't think. It's Mark Azar, who is our, you could say, optimization expert at EQUA. And we will, this webinar, as you probably know, is about optimization. And this brings us to the third main goal of IDICE 5. And this is also the concluding webinar for the series that we've held for the release of IDICE 5. So in the first 4 webinars, 5 actually, including the initial webinar, you've seen that IDICE offers a lot of new features for predicting what goes on in a building. But as you also know, this generates a lot of questions, and that's kind of the purpose. And the third leg here we're standing on is optimization and the cloud. And the cloud, as I mentioned before, brings us enormous possibilities to compute massive numbers of cases, and it'll cost typically maybe 10 euros per hour to rent 100 cores in the cloud, which might be a suitable number for many optimization exercises. So it's not prohibitive in any way, but still, even with the power of the cloud and all these processors, we will still have problems in the sense that it's still not possible to explore the whole parameter space. Actually, I don't see my own screen anymore here. Sorry, I'll fix this. There you go, I think. Sorry, I'm having some problems here. And so we will still not be able to investigate the whole parameter space. We just have too many parameters to even with some resolution find the optimal answers in this. And that's where optimization comes in, an algorithm that smartly finds the interesting regions for us to explore in this parameter space. And the thing with optimization is that it's very easy to find optimization algorithms, but most of them will have a lot of parameters, tuning parameters, and it's also very difficult to select what type of optimization algorithm you get. And this is where the automatic in Automo comes in. So Mark has built a system where you can just decide on the number of simulation runs you want to spend, because that's directly related to the costs you're willing to spend. And Automo sees to it that these runs are spent in a close to optimal way on finding the results. You also have to decide on the size of generation, how big the pool of computers you want to use for each generation. And this has to do with the physical time that you have access to. So let's say that you set this up in the evening and you have maybe 12, 14 hours until you want to look at the results. Then you can look at how many generations do you want to spend in finding the result until you get back in the morning, basically, depending on the length of the simulation. And multi-objective is, most people are familiar with this concept, that single objective optimization, you're trying to find a single number which is the best fit for one goal function, basically. We've seen some such examples in the past. Multi-objective is actually more relevant in most practical cases, because you're nearly always looking at a cost-benefit situation. So there is a cost in terms of perhaps dollars and euros, or it could also be in terms of investment cost, fuel costs, and so on, versus a benefit in terms of indoor climate usually, and quality indoor environment. So there's always this trade-off, and that's what the multi-objective is all about. Generally, we look at two objectives at the same time. I think most of you have most presentations on multi-objective is on two objectives. So in this case, we'll show that you can have a lot of objectives, and that's very interesting as well. And then the last part of what we have been trying to achieve here is interactiveness, because you spend a lot of time deciding on what parameters to optimize and to formulate goal functions about what you want to achieve with this optimization. But it's nearly impossible to do this right the first time, because you start to explore and then you will find that you actually should be looking at some other region of the parameter space than you thought you should. And it makes it necessary to look at this as an interactive process. So we really try to create an interactive environment here where the next Automo experiment will benefit from the runs that you've already spent. So with that, I give the word to Sven to start this demonstration, and he will show you a practical case. And then after that, Mark will go through some more background to Automo and theory. Thank you. So over to you, Sven.
Thanks, Per. Do you see the correct screen now?
We do.
Great.
I hope.
So, yeah, I would like to give you an idea about the unexpected possibilities with Automo. And in doing so, I would actually also like to encourage you to try any example yourself without thinking at any limits. So personally, I am always fascinated by the idea that, for example, the building technology has to adapt to the design of the facade. Which means that when optimizing a facade, the optimal building technology will vary with the facade options, and both have to be optimized together. So my fixtures example here is a large office building in Stockholm, and the future building owner's idea is that as much as possible of the energy used for the building should be produced locally on the facade. And here on this picture, you see the yearly insolation on these facades. So after these initial preliminary studies, it was decided that on the longer west facade, the space between the windows should be fitted with PV modules. And on the shorter south facade, the space should be fitted with thermal solar collectors. The heat for heating and domestic hot water will be provided primarily by these solar collectors, of course, and only if necessary by an ambient air heat pump. The main question is in which relation the window areas should be to the module areas here. And for this purpose, I have defined some input parameters in my optimization. I'd like to open those. Here you go. Yeah, so for instance, together with the solar width here in the western facade, also the PV model width should be varied with a single input parameter. So I defined this one here, and you see when I change, there is quite some graphical scripting, and it will adapt everything here. So this is a low window width versus a very, very large window width, of course. And you see some time is needed for this calculation here. So let's do maybe switch back to a medium window width. Yeah. Of course, we expect a direct correlation of this parameter with the amount of solar power produced annually, but also with the power consumption for the lights, for instance, in the offices. And both those have an influence on our first objective function, the self-sufficiency for electricity. So that's a number that tells us what proportion of the total electricity consumed could directly, so at the same time as production, as consumption taken from on-site electricity production. And for the south facade, we also defined the window width as a parameter. So here it's the same thing. I vary this parameter, and you see that the windows and collectors are adapted simultaneously. Together with the size of the collector field, we also vary the size of the tank. This is now a direct parameter here, so I can vary this tank size here. And I'll go back to my inputs. The last thing is the solar pump mass flow, which also can vary with optimal solution here, together with the solar collector size. So this is the area-specific solar pump mass flow, and you see here the parametric, the graphical scripting, for instance. So the width of south windows. From there, just calculate the width of collectors multiplied by the height. You will get the area of the collectors, and this is multiplied by this area-specific mass flow to get the absolute mass flows, of course. So in our optimization project, we now define the following input parameters. Here we go, the south window width, the PV model width this is the solar thermal collector width will then vary together with that, the west window width, the tank volume size, and the area-specific solar pump mass flow. The building is then to be optimized with respect to daylight, the daylight that is to be maximized, also thermal satisfaction rate here to be maximized, and the total electricity consumption to be minimized, and this important goal function for the building owner, this self-sufficiency rates to be maximized for both electricity and of course heat, that is the proportion of heat that is taken from solar collectors. Beside these optimization goals, we have other output parameters that we simply want to display. So there the role is set to show, and these are the shares of the total electricity need for cooling, heating, and light, and the total yearly annual PV production is also interesting for us to look at the result. So as you know, we can do different parameter ground types with the same setup. We have the Monte Carlo and we have this optimization run where we have the Automo option here. Monte Carlo simulations have the advantage that all 120 cases can be simulated in parallel when working on the cloud, while Automo will only run a limited number of cases in parallel and then use the experience from those to decide about the parameter input sets for the next generation of cases. This will cost more waiting time, but it will save total CPU time, and that is what costs, or what will cost you. So yeah, so let's now look at some results. On all these 4 diagrams, we do have 1 dot for each of the 120 runs. The total purchased electrical energy is on the y-axis. This is the parameter we want to minimize, and self-sufficiency is on the x-axis. That's the parameter we want to maximize. So our optimal cases are on the lower right corner. Self-sufficiency for heat, you can see to the left, and self-sufficiency for electricity to the right. The colors indicate the window width. Of south windows to the left, there's those between the thermal collectors, and of west windows to the right, that's those between the PV panels. In all 4 diagrams, we see a strong correlation between window width and self-sufficiency. So you can see the blue dots to the right and the red dots to the left. And this does not surprise. Actually, low window width means high panel size and means high self-sufficiency. The difference between the Monte Carlo runs and the Automo runs, so Automo to the top and Monte Carlo to the bottom, do not seem to be big at the first glance, but we can, for instance, find more dots in the lower right corner where the optimal cases are, like here, and also here, compared to the lower diagrams. We can also look at the same diagrams to the left here, but with some different color settings. The dot area now indicates the tank size, and the color indicates the solar pump mass flow. And just, yeah, we can see a much more obvious difference now in dot colors between Automo and Monte Carlo, without maybe that, yeah, maybe we don't understand that clearly first, but there is a difference. For the optimal solution, it seems that Automo decided for either high or low flows, high flow, which are red, and low flows through the solar pump, which are blue. But this is somehow difficult to interpret, and that's why, yeah, in general, with this kind of graphs, it proves difficult to draw the most valuable conclusions here. And that's why, once more, I want to show you the ultimate result presentation for optimization studies with many runs. And that's the parallel coordinate plots. Let me see where I have them. Well, maybe I go to results here and I can explore this. So for those who are not used yet to these, I can quickly repeat. You can see here each line in this graph represents a set of input parameters. So this line goes along all the parameters, the 4 input parameters to the left, and our 9 output parameters to the right. And if you look at all these lines, these 120 lines, we can immediately see something like a path of optimal solutions here. And yeah, we can now start to set limits to selected parameters, like we want to look at low total electricity consumption only. And of course, we want to have these high self-sufficiency heat and also high self-sufficiency electricity. When we then set the color to the solar pump mass flow, we can see 2 families of optimal, like two local optimas of this problem. So we have high flow systems for the solar collectors and low flow system for the solar collectors. And you see that the high flow has maybe the advantage to have a higher self-sufficiency in heat, but there is a disadvantage of having higher total electricity consumption. So yeah, we don't know yet. Is it the pump electricity for pumps, or is it something else here? So let's now check what we can find out with the same number of cases with Monte Carlo method. So I have open here the same cases where I did run a Monte Carlo instead, and I can explore the same graph here. And the first thing we see is that we don't see this path again, but still we can try to select the same region of total electricity consumption, and then limit here the cases for self-sufficiency and set the color on pump mass flow. And yeah, this is maybe quite obvious now to see the advantages of Automo. So yeah, the last thing maybe I want to explain, I will go back to my parametric run. So when carrying out your optimization project, you will probably want to look at your results after the first couple of runs already. So I just recommend to start maybe with a rather low number of runs. You can then look at these results and adapt your input parameters. So you can adapt the ranges here, for instance, and you can exclude some goal function and include others if you want. You can set constraints and then restart your optimization. Just don't forget before restarting to set these clear results from previous runs to know, in order that your optimization routine don't forget what it already calculated. And this makes an optimization project very interactive, what we think is actually the right thing, because IDEs will never take over the task of thinking from you guys. But we hope that it can support you in finding the solution that you think is the optimal one. Yeah, that was my case. I hope it was illustrative, and I can now hand over to my colleague Mark Azar, who did this fantastic job and developed this Automo implementation. Please, Mark.
Yes, thank you, Sven. Let me share my screen here. There we go. Okay, thank you for this interesting sharing with us, this interesting presentation. My name is Mark Azar, and I'm the developer behind the newest optimization tool in IDEs, Automo. Automo was developed with the intention of being a simple yet powerful way of running optimization cases. So in the next 15 minutes, I'll talk a little bit about some of the features that are supported by Automo. And for those of you out there who are already helping us test IDEs Beta 5.0, you're probably already exposed to some of those features we're going to talk about. I'll also discuss slightly the concepts behind what makes Automo a powerful and flexible tool. And I'll end with a small run-through of the Automo-specific items in the parametric runs interface that Sven just showed us some in the last slide. So let's start. Automo, first of all, is a single-click optimization engine. So that's not to say that you won't have to take care in setting up the optimization case, carefully selecting the parameters you wish to optimize and the objective function you want to optimize against. But it's to highlight the fact that with Automo, as Per mentioned, that you won't have to deal with the selection and configuration of any optimization algorithm. So Automo does not require any technical knowledge from you guys in any optimization theory or any optimization algorithm. Automo also by design will always ensure that you have a high efficacy in its search path for the optimum point, rivaling any expert. And we will come back to this point later on in the next couple of slides to discuss why that is the case. Why are we so confident in this? Automo will also automatically detect the type of optimization being conducted. So whether it's a single optimization or a multi-objective, and it will run accordingly. Automo can handle large optimization cases, so with thousands of parameters and hundreds of objective functions. Automo's results are also reproducible. So at any point in time, if you wish to rerun the same optimization case using the same parameters and objective functions, you'll always yield the same search path and the same optimum result. And this is very important for consultancy work to be able to reprove your work. Automo is designed to run sequential batches in parallel. So Automo would run select batches of cases, let's say in the order of 10 or 20, and would run those in parallel. It would, and this by design would benefit from cloud computing, where hundreds of cases can be run in parallel, while also giving you exact and precise control of the optimization experiment with cost-benefit analysis, as Per mentioned. So we'll later on come back to this and show you how exactly the user is able to control the number of runs based on the resources you wish to allocate to the optimization case. So Automo is an excellent decision-making tool, and it's capable of supporting soft constraints on objective functions to be able to steer the search path towards viable solution. With Automo, you're able to stop, to pause, resume an optimization at any time. Moreover, you'll be able to load previously saved results and make use of those without having to rerun them. So this is something Sven mentioned quickly, and this is a really interesting feature. We'll also come back to this in the next couple of slides. So this is a list of some of the features that that Automo have. But for now, you know, what is Automo really? We've mentioned some of those features, but you're probably wondering, like, how does it work and what's under the hood? To understand this, first we need to take a little bit of a look at the very nature of what makes an optimization problem difficult. Here to the right, you can see a typical search space. This figure here, you can see a typical search space that is generated by the combination of two parameters, x1 and x2, and a single objective function f of x. The optimization is basically about finding the best set of parameters, x1 and x2, with accordance to a set of objective, in this case f of x, under a given set of constraints. The constraints in this case are given by the ranges of x1 and x2. And the optimum, as you can see in the picture, is located somewhere here in the valley point. Now, it's clear from this that a building simulation search space is no easy task to navigate. Something that is filled with shifts and discontinuities is very hard for any automated algorithm to navigate successfully and find an optimum. So that hasn't stopped optimization experts from creating many different methods and many different approaches targeting different challenges in search space navigation. And each approach excelling in certain regions of search space navigation, while others yielding better results under different regions. We have a list here of examples like grid search algorithms, gradient-based, evolutionary, heuristics. Probably some of you out there also have experimented in some of those algorithms. But what makes Automo powerful is Automo is basically very simple in nature. Automo doesn't compromise. Automo incorporates multiple robust and proven algorithm and approaches in the field, from evolutionary to genetic, as well as meta models, used in various industrial fields, from AI to neural networks, CFD, and aeronautics. So basically, why not run them all? By combining these approaches, 6 in total at the moment, and more to be added in the future, Automo adaptively rates each algorithm's performance as the optimization is running to select those that are best performing. And this is why you will always end up with the best of the best. When every simulation case, every dot there on that figure, on the black figure here, every dot represents a simulation case, basically a run in eyes. So when every point there is expensive and must count, Automo's approach becomes very evident. Why not choose to create and update all available algorithms, all available optimization algorithms, whose computational cost pales in comparison to a single evaluation point, to a single IDA run? And that's why with Automo, you will not be settling for any single algorithm, but you will, and you will not be compromising. So in essence, Automo is merely a voting algorithm. It's a voting algorithm that ranks every optimization algorithm under its hood to create a pool of possible search areas from the best ranked approaches, but without neglecting the worst ones. Why do we do that? Why don't we neglect worse ones? Well, we know that different approaches will work best in different search regions. Therefore, well-performing algorithms at one point in time in the same optimization might perform poorly at a later stage, and vice versa. So the vote is always re-evaluated with every generation, and all algorithms are updated with the best results. Now, finding the most efficient search path has always been about finding the best balance between exploration and exploitation. To what extent we should expand our search space to include new regions versus to what extent we should rely on previous results to narrow our search space and select to selected regions. And here the cloud is perfect in helping us address this challenge. The cloud is pretty capable of running hundreds, if not thousands, of parallel children per generation, thus expanding our explorational abilities and therefore requiring Automo fewer generations to reach a global optimum. So we are basically saving time by using available computational resources. Okay. Let's take a little quick look about the additional input fields that are dedicated to Automo in the parametric runs interface. Now, aside from the normal input fields that you usually use to create or set up a parametric runs case, like Sven showed, the selection of parameters and their ranges, the creation of objective functions with graphical scripts optionally, Automo has added a couple of neat features, such as the first one that also Sven mentioned quickly is this over here, clear results from previous rounds. So this takes a yes/no input. When it's yes, basically the optimization run will start from scratch. But if you do select no on this, you enable this enables you to feed Automo basically previous results that have already been simulated. Let me emphasize this for a moment. These previous results, they can be from a Monte Carlo, they can be from a parametric runs, or any other optimization run. And I'll elaborate a little bit more. You're able to change the ranges to narrow down the range of your parameters or widen them and rerun without clearing previous results. What will happen is Automo will automatically take in the previous results, filter out the useful ones, and use those in the new run. You'll never again lose valuable evaluations, even in case of failure, numeric or bug. Save your results, reuse them in the new Automo run without having to rerun them. So this enables you full control of your optimization, narrowing down and widening your ranges incrementally. Moving on, I'd also like to mention another little nifty option called precision here, highlighted there next to resolution. So precision allows you, as its name suggests, it allows you to set a limit on any parameter in terms of its precision. It takes an integer and that indicates the number of digits to take into account at the right-hand side of a decimal point. So a 0 here indicates that Automo will treat this parameter as an integer, even if it is logged in IDIs as a float or real. And a value of 1 means Automo will treat this parameter as a real with a single digit after a decimal point. Why is this nifty? When should we use this feature? Well, when the physical parameter is limited in real life, think of, for example, currency. In currency, the lowest digit is a cent that we need to consider. Optimizing any further than that is a waste. Or when you would like to narrow a range of a real into a smaller grid size, then that could be beneficial and used. But we beware not to overuse this feature on every parameter, even when you don't need it, because integer type optimizations with large grids are in general harder than smooth real ranges optimizations. In the lower window here, we see that there's a input field called role. And this role can take an input called show. And show, as Sven mentioned, indicates that this function will not be used in Automo and will only be available when displaying results later on. But it can also take a const input. And this indicates that this function that you just labeled as const is a soft constraint function that you created. Automo will automatically then evaluate the quadratic distance, the extent from which this constraint is violated, and add automatically on all other objective functions, those marked with min or max, this penalty. So this allows you to furthermore steer Automo into certain design decisions that are only you're interested in. But speaking of which, it is important here for you to set up these objective functions in a meaningful way. Even if Automo is very flexible and forgiving of bad starting points, it helps when you properly set up your optimization case. So for instance, the objective functions, they're always preferred to be normalized or to be of the same order, more or less, especially when you're having more than one objective function. It is not recommended, for instance, to have an objective function with an order of magnitude, let's say in the thousands, and another one, its order of magnitudes is in the decimal range. So to help you in this task, what we did is we have two more input fields here, one called min and the other max. And Automo will use those if they are filled to normalize your objective functions. So you don't have to manually normalize them in every graphical script. Now, finally, you will have to choose how many cores you would like to allocate for this optimization run. And this is found in preferences in the settings in IDA. And how many total number of runs you would like Automo to conduct. And this is displayed here in the bottom under total runs. So to clarify, if you choose 100 total runs as displayed in this picture, Automo will always run in total 100 cases, regardless of how many cores you chose in those settings. You will always end up with around 100 cases. So if you know your budget can only account for 100 cases, set this number to 100 and you'll always end up with 100. You won't overspend. But if you choose to have more than one core allocated to the optimization runs, let's say 10 dedicated cores, then those 100 cases will run in a parallel batch of 10. So they will only produce 10 generations, reducing the total optimization time to an equivalent of 10 simulation runs only. Automo benefits from having a large number of cores running batches in parallel. The more evaluations you run in any single generation, the better Automo's future guesses will be. So in general, you will need at least 2 batch runs to reach any meaningful optimum. But the larger your search space and the more objective functions you want to set, the higher number of total runs that will be required to achieve an optimum. Now, in our internal testing, As Ben showed, Automo has exceeded our every expectation. And you only have to test and try it out to get a feel of how powerful Automo is in helping you make better design decisions with a single click. So I encourage everyone here attending, go ahead, give it a go, and help us by reporting back bugs to our awesome support team. I'll stop here for today, and thank you for your time. And I think we'll open the floor for Q&A now, Patrick. Thank you.
Okay. Yes. So there's already some questions coming in. Please raise your hand if you want to ask a question. We will take a look at what's come in. I've tried to answer some in written form here, but I can repeat them here perhaps while you're thinking of other questions to ask. So one of the first questions, somebody said good morning, or Mario Lici. Good morning, everybody. I hope you said that.
Bonjour.
What are the advantages of using Automo versus Genopt? Genopt has been available in the parametric runs for some time, and Genopt clearly has some advantages also. It's very good, but it's not designed for this sort of parallel. I mean, there's two major differences, you could say. One is that Genopt is single objective, or three perhaps. Genopt is single objective, so you can't really look at multi-objective runs using Genopt. It looks for a single objective thing to optimize. I hope we've explained that this is a bit limiting. The other one is that it's really designed for limited number of cores, so it will take advantage of parallelism initially in its process, but after a while it generally switches to some steepest descent type of algorithm where it will only use one core in one experiment at the time, and this becomes very limiting, especially on the cloud when you want to use all that computational power that you have. And the other thing with Genopt is that I think most people, including myself, use it pretty much only with the default settings, and Genopt actually has a whole language for tuning the optimization algorithm, but if you take a look at the manual, you see that it's not so simple to select and tune that algorithm in the best way. So I hope that was the answer to that question.
Maybe we should also mention that internally in our tests, comparing Genopt and Automo, usually with the default configuration of Genopt, it usually takes around 300 runs to reach an optimum, while Automo does that in order of tens.
Yeah.
So
it's
much easier to use.
Yeah, it's easier to use, but it's also difficult to compare these things in a fair way, I think, because it has to do with
default configuration of Genopt. Yeah.
And that brings us to another question, which is or if there are any. The question is, are there any benchmarks for Automo with versus other optimization tools in terms of how efficient it is in terms of number of runs and so on? And I guess we're not aware of any such clear benchmarks where that compares likes for likes in terms of simulation algorithms. It might very well exist, and if somebody knows about them, please let us know. But the setting here that we would like to explore is that of the cloud, so having access to a lot of parallel computing power, basically. What's done on the sequential machine is less interesting, actually. Let's see. Then this is only available in IDA 5. Somebody wondered. How does
it's out in beta as well, 5 beta as well, right?
It's out in the i5 beta, and I guess as with betas, always use the latest one because there's going to be lots of bug fixes and also some small feature enhancements along the way. Then there's a question about the. Do you see that, Mark? How does Automo choose which optimization algorithm it uses for selecting the actual cases?
Right. So that's the beauty of this. It doesn't. It runs all of them all of the time. I'll reiterate this. So at the moment, it has 6 algorithms under its hood running: genetic algorithms, meta algorithms, and it runs all of them for your cases. It keeps voting on those 6 algorithms, and it ranks them, which is the best algorithm and which is not doing so well at each generation. But it always will run all of them and will always update everyone, and it will keep on listening to all of them, because you never know which algorithm will start outperforming the other at later time in future generations. So that's why it doesn't compromise. When I say Automo does not compromise and will always yield the best of the best. So rest assured, it runs everything.
Sorry to interrupt, but we have a live question from Mark Labros. Sorry, I'm gonna go ahead and unmute you, Mark.
Was I muted?
No, other Mark.
That would have sucked. I was talking for an hour, man.
So Mark Labros, you're still self-muted. So you need to unmute yourself. Yeah, there we go.
There we go. Okay, sorry. I just have one question in terms of this optimization. So I'm personally trying to run a study where I'm investigating different kinds of external shading devices. And so in this connection, I'm of course I'm looking at 2 different kinds of glazing, and then a set of different external, Venetian blinds, micro shade, some different kinds, and also some louvers that are fixed at place but can rotate. And so the problematic here is that each shading device needs a specific shading control. So for a screen, you can activate it just by knowing the effect of the sun, but for the ones that rotate, I need to know specifically where is the sun located to know how should I rotate my lamellas. So if I were to do a parametric run, I would put 3 inputs. I would put my glazing, I would put my shading type, but also my control. But essentially, as you can see, this would create a lot of simulations that doesn't make sense. So for the screen, it would do some simulations with a control that is made to, choose the angle, and there's no angle for a screen. So my question is whether is it possible to pair parameters, saying that this kind of control is set for this kind of shading device?
Do you want to pick this up, Sven, maybe?
Well, what comes to my mind is to do this with a graphical script. So find a parameter that can describe your combination. Or maybe have even a table where you can mark combination that are not allowed or something like that. But you need to. Well, that would be my solution. I maybe.
But basically introducing a new parameter that selects both the screen type and the solution algorithm at the same time, and then introduce that parameter as an enumeration to the optimization algorithm.
Okay. Smart. That makes sense. Thank you.
Great. Any other questions? Live here.
No more live questions at the moment.
Right. There's a question from Victor Fransson. He says that optimization problems require some kind of fixed situation. How well does the method work with the approach incorporating uncertainties in the input data, such as variations in indoor climate and uncertainties connecting to human behavior? So basically, there's nothing stopping you from treating, for example, the climate file also as a parameter that can be varied and uniformly distributed. I guess it's not total. I mean, in the Monte Carlo sense, this is quite straightforward. I think they would then just randomly select the parameters that you want to look at, and also other types of inputs that in practice will vary. I'm not 100% sure if it would be possible. I suppose what you would really want is to distribute those kinds of parameters uniformly while optimizing some variables at the same time. I'm not sure that this is possible. Do you have any comment on that?
I think that the classic approach is to study post-optimization, how the change in input affected the change in output in the optimization. So you would have to change your input parameter range a little bit and then run optimization, full optimization again, get your output, then change a little bit, run full optimization, get your output. And then you study how this change in input changes your optimization output to see how sensitive your output, your optimization output is to a change in your input. So this is something that requires multiple optimization runs, full optimization runs, and it's a post-processing option that is usually done classically when you want to approach these things. There's also a question before that from Christoph Horvath about which calc methods.
Oh, right.
Very, very good question. That's sort of the secret sauce in our Automo, and as well as how we vote on those. So I can't diverge too much. I can tell you that today we're using 6 very well robust and well-used models for optimizations and algorithms. And in the future, we'll be keep on adding more and more. I personally do the filtering and choosing of those algorithms, depending on how they perform in under similar tests for simulations, because not all algorithms are meant for the same problem. A black box problem with global optimum, wanting to find a global optimum. So I do the filtering out and I sort of tweak those votes and those algorithms. And that's why I need your guys' input and feedback to make Automo always improve. Another also question from Christoph, I'm just following off, is there any monitoring possibility to see the processes or the performance of the algorithm? You can see each and every algorithm's performance, but it's not yet, we have the data, but we haven't yet provided a interface for the user, because if it's we would like to hear from you if this is something that many of the attendees want to know, which algorithm is performing better than the rest, and maybe you want to run your own benchmarks on these algorithms, then we could add that to the interface. So we have the data, but we don't show it, basically.
Right. Urs Grossenbacher has a straight but very clear question here. How much does it cost for the cloud computing? And it's on the order of about, I mean, it depends on the machine that you will select for this pool. We will select some machines for this. There'll be some different types of pools in the cloud offer. We'll come back to that. But for typical machines, it's about 10 euro cents per core per hour. So it means that 100 cores for an hour will cost you 10 euros. The cloud is the cloud already available for the beta? Was another question. This brings us into the sort of things that we wanted to talk about towards the end here. We're approaching the end. The cloud, we're not quite at the stage where we can invite beta testers into the cloud. My ambition is to get there as soon as possible, but there's always another feature that needs to be implemented, and there's also since this will cost money for you guys. I mean, you're going to have to be paying for the actual hardware costs. Even the beta testers, we need to set up a sort of a foolproof system for invoicing and so on, and that's one of the main things. All of these pieces are actually in place, with maybe one or two exceptions, but we're in the process of refining it and deciding when it's good enough to release. But ambition is to do this soon after the summer. And on the cloud, IDA-ICE will only be IDA-ICE 5 on the cloud, so you will not. There's a lot of things. I'm not going to go into them. That makes it difficult to have older versions of IDA-ICE on the cloud.
Okay, I just wanted to mention that IDA-ICE Beta 5 is already out, and you can contact support, I guess, to be a tester and have access to the Automo features.
Right.
There's also two technical questions I would like to answer.
It's available at the moment. It's available only for maintenance customers. We should add, yeah.
Yes. Become a maintenance customer then.
Yeah.
It's worth it. Automo updates all algorithms. A question from Jan. Does this mean that it actually runs all simulations? No, it updates them, but then when it ranks those algorithms, it will weigh the ranks and then take a certain number of guesses from every algorithm according to the rank. So it will favor the higher ranks than the lower one, but it will never neglect the lower ones. It will at least take one option from the worst because even the worst squirrel will find a nut every now and then. And another question there is, how are the different output objectives prioritized in Automo? There are weights that you can set weights on objective functions, or you can use the graphical script for that. What about GenOpt? GenOpt doesn't prioritize because you can only set one objective function in GenOpt. Yeah, I think Sven, there's a question for you then for the special webinar. Optimization for facades. That's a request.
Oh, I didn't see that. Okay.
From Jan Kruger.
Okay. Great.
Yes, weighting between objective functions is something Alexander Lindblom is interested here. Maybe that's some of these questions are a little bit beyond what we can address here, I think. And the cost for the end users for using the cloud. In the first, if you look back in the webinar recordings towards in the end of the first highlights webinar, we went through the target pricing for using the cloud. I realize it's going to be a monthly subscription, so it's not going to be like an hourly use fee that we had thought about in the past. It's going to be monthly, and the approximate cost for using IDA-ICE in the cloud, our ambition is should be neutral to what it is if you don't use it in the cloud, basically. But then, of course, the actual core, when you make these large simulations, you will also pay for simulation costs, like I said before, on the order of 10 euros per hour for 100 cores, for example. And then Dirk Jacob has a question that we meet a lot. The question is whether we will allow sort of people to set up their own clouds using their own existing computational resources. We're aware of that many people have built such computational resources, and the answer is that we will not prioritize this in the beginning, but rather you will be IDA-ICE will only be available on the sort of IDA-ICE or on the EQUA cloud initially, at least. That's the way we look at it now.
There's a question about where our cloud is located.
Azure, yeah. I don't know physically where the servers are, but it's on the Microsoft cloud now. And yes, about special webinars, maybe Sven could have a facade. It sounds like very interesting to have a facade optimization webinar. I think that sounds like.
Well, yeah. Well, here I can also tell that my example it's a difficult one. I did not succeed in doing it completely by myself. I needed some help from our developers because these PV models, you have really to take care what it means if you resize the model, because there are plenty of parameters and these must be adapted. And yeah, that was not easy. Actually, it was a case where I recognized some feature need maybe for these kind of projects, but yeah, it's of course a good idea to think about such a course.
Yeah. Right. So here's a question from Jonathan Niemann, whether you can replace entire systems like air handling units and so on as a parameter. I'm not 100% sure, actually. It should be possible. I absolutely agree that this is a very important thing to be able to do. And I'm not sure that it's possible today in any simple way, but we will absolutely make sure that this works. That's a key thing to be able to do. And with that, we've already used a couple of extra minutes here. This actually concludes our webinar series. We've managed to keep your attention in large numbers for 6 webinars about IDI's 5, and as you've seen, there's a lot to talk about, and there's still more to talk about, but we will have to stop it at some point. And this concludes our webinar series on the IDI's 5 release. And we actually don't have any fixed date yet for the next set of webinars. We know of a couple, like there will be one on facade optimization for sure. I think that's a very good idea. And another webinar that we know for sure is once we actually release the cloud environment, which is not very far away, we will have a very practical webinar just to show you the ropes and go through all of the steps and where you enter what and so on, how it works with the cloud, basically, including pricing both for the beta phase and for the future. With that, I thank you all. We will send out an email with where we fill in some of the questions that we weren't able to answer live here, and also not an invitation to the next webinar, but you'll have to wait for that. Okay, thank you everybody, Sven and Mark and all of the attendees. Thank you both there.
Thanks from my side.